Have you ever tried to imagine the exact moment Earth lets you go? Not the launch, the fire and noise and shaking metal. I mean the quieter betrayal that comes after. The point when the blue-green glow is no longer a world around you, but a coin behind glass. A memory with clouds. We like to pretend the solar system is a neighborhood, a few familiar streets. The moon is right there. 3 days. Apollo proved it. So our brains do what they always do, they round the rest down. 10 days to Venus, a month to Mars. Surely the planets are just farther stops on the same route. But space is not a map, it is a clock. Every destination you can name is moving. Every distance is an argument between two bodies in orbit, sliding past one another on ellipses, sometimes leaning close, sometimes pulling away like strangers. If you leave Earth and aim straight at Mars by the time you arrive, Mars will no longer be there. Not because it vanished, because you misunderstood what a planet is. A planet is not a place, it is a point on a racetrack. And that's the paradox that turns interplanetary travel into something almost poetic in its cruelty. Going fast is easy, arriving is hard. In a vacuum, you can't slam the brakes. There is no air to bite, no friction to save you. If you want to stop, you must spend energy to cancel energy. You must burn propellant, your stored finite violence, until your speed matches the world you're trying to meet. Miss that match even slightly, and you don't arrive. You fly past. You become a brief visitor, a streak of instruments, and hope gone into the dark. So when we ask how long would it take to reach the planets, we're not really asking about time. We're asking how well can we negotiate with gravity. Because gravity is the true transit system of the solar system. Engineers don't drive straight. They choreograph. They slip into curved paths, those elegant transfer orbits that look like a dancer's arc. One push, one long fall, and a rendezvous planned months in advance with a world that refuses to hold still. Sometimes they add another trick, a gravity assist. A flyby so precise it feels like theft. You skim a planet or a moon and steal a fraction of its orbital momentum, gaining speed without spending fuel, like catching a moving train by brushing its handrail. This is how we travel between worlds, not by brute force, but by timing. Windows, angles, patience. A physics ballet where a single misstep means millions of kilometers of empty correction. And today, we're going to take the grand tour, planet by planet, world by world, not as a fantasy of straight lines, but as it truly is a negotiation with a moving solar system. By the end, the night sky won't look like a scattered decoration anymore. It will look like machinery. It will look like distance. And it will look, if you let it, like vertigo. Before we can talk about Mercury's 4-month shortcut, or Mars's 9-month endurance test, we have to confront the thing most people don't feel when they look up the solar system is not arranged. It is in motion. The planets do not draw perfect circles. They ride ellipses, stretched loops with a closest point to the sun, perihelion, and a farthest point, aphelion. And they do not move at the same pace. The farther a planet is from the sun, the slower it drifts along its track, because the sun's gravity loosens its grip with distance. In other words, the bus stops are moving, and the buses are moving at different speeds, and the routes themselves are curved. So the phrase, "the distance to Venus," is already a small lie. Sometimes Venus comes near enough to feel like a lantern hung beside Earth's orbit. Sometimes it's on the far side of the sun, unreachable in any practical sense. The same is true for every planet. There is no single number. There is only geometry, an ever-changing relationship between two clocks on different gears. This is why interplanetary travel isn't about pointing a rocket and pressing go. If you did, you would spend most of your fuel trying to correct a mistake you made at the start, assuming the target would wait. Instead, mission designers use curves. They aim for where the planet will be, not where it is. The simplest, most elegant version of this is the Hohmann transfer, an elongated orbit that kisses Earth's path on one end and the target's orbit on the other. You don't fly through space like an arrow. You fall around the sun on a new ellipse, and months later, if you timed it correctly, you intersect the planet's lane at the precise moment it crosses that point. And timing isn't optional. These transfers create launch windows moments when the relative positions of planets are just right. Miss the window and you wait. Days, weeks, sometimes more than a year. Mars, for example, offers its best efficient departure chances roughly every 26 months. Not because Mars is stubborn, but because celestial mechanics is. But even a perfect transfer has a second problem, and it's the one that quietly governs everything you're about to hear. Speed. To change your orbit, you must change your velocity. Every extra kilometer per second costs an enormous amount of propellant. Rockets are unforgiving accountants. The more speed you demand, the more mass you must spend to carry the fuel to get it, which means more fuel to carry that fuel and more fuel to carry that until you realize why space travel feels like building a skyscraper out of gasoline. So engineers reach for the greatest loophole available: gravity assists. A spacecraft swings behind a planet like a surfer dropping into a wave. In the planet's frame, the craft comes and goes with almost the same speed. But in the sun's frame, the planet is moving, and the spacecraft can steal a tiny piece of that motion. A few thousand kilometers per hour gained without burning an extra gram of propellant. Not magic, just momentum, traded with surgical precision. And here's the brutal truth that makes the whole solar system feel farther than it looks. Flybys are comparatively easy. You can arrive fast, take a picture, and leave. To stay to enter orbit, you must arrive slow enough to be captured. In a vacuum, braking is expensive. Braking is a mission. This is why two journeys to the same planet can differ by years. One mission rushes through as a passerby. Another crawls in, patiently shedding speed, arranging assists, enduring long arcs, because the goal isn't to visit. The goal is to belong. Keep that in your mind as we begin the tour, because it will repeat like a law: distance is not the enemy. The enemy is the speed you must lose when you get there. If you want the quickest way to feel how deceptive the solar system is, aim for Mercury. On paper, it sounds simple. It's the nearest planet to the Sun, and often one of the nearer planets to Earth. You might think it's the easiest neighbor to reach, just a shorter drive inward. But Mercury is where spaceflight teaches its first cruel lesson. Getting closer to the Sun is not like walking down a hallway. It's like stepping onto a faster conveyor belt. Earth races around the Sun at about 30 kilometers per second. Mercury, deep in the Sun's gravitational well, moves faster, around 48 kilometers per second. To arrive at Mercury, you don't just travel a certain distance. You must change which orbit you belong to. You must shed a vast amount of orbital energy to drop inward without slingshotting past the planet like a stone skipping off a river. This is why flying fast is easy and arriving is hard. We can build spacecraft that move astonishingly quickly. The Parker Solar Probe, on its close passes by the Sun, has reached speeds that make everything else feel slow, hundreds of thousands of miles per hour. And yet, even with speed on our side, the optimistic travel time to Mercury still lands in the realm of months, not days. Because the mission is not go, the mission is go, and then lose enough speed to be caught. And Mercury is stingy with help. Unlike Mars, it does not offer a thick atmosphere you can dip into for aerobraking. There's no forgiving air to steal your momentum. Near the Sun, the heat and radiation are punishing, and the margin for error is razor thin. If you overshoot, you can't just turn around. You drift into a new destiny. So we do what navigators have always done: when brute force fails, we cheat with gravity. Mercury missions read like choreography notes. In 1973, Mariner 10 didn't charge straight inward. It used Venus as a stepping stone, one precise gravitational boost, and reached Mercury for its first flybys after roughly 6 months, giving humanity its first close-up look at that cratered ancient face. Decades later, Messenger launched in 2004 and performed something that feels almost like stubbornness, embodied multiple flybys of Earth and Venus, then Mercury itself, again and again, bleeding off speed in tiny, deliberate installments. It took about 6.5 years to finally enter orbit. 6.5 years, not because engineers were careless, but because they were economical. Because in space, the cheapest fuel is patience. And even now, Bepi Colombo, the joint ESA-JAXA mission, launched in 2018, follows the same logic with modern tools: solar electric propulsion, continuous gentle thrust, and a long chain of gravity assists with Earth, Venus, and Mercury, all to solve the same riddle. How do you arrive slow enough to stay? Which brings us to the deeper reason Mercury matters. It is small, yes, but it is dense, an outsized metallic core, an active magnetic field that shouldn't exist so strongly in a world so little. Its battered surface is a fossil record of the early solar system's violence impacts, volcanism, crustal scars. Studying Mercury is not tourism. It's archaeology at the edge of the sun's forge. And the paradox is that the planet closest to the sun, closest to the source, demands some of the longest, most careful journeys to truly know. Mercury teaches the rule we will carry to every other world. The hard part isn't crossing the distance between planets. The hard part is changing the kind of orbit you are. Then we turn our face away from the sun's glare, and Venus rises like a promise. It is the brightest star after the sun and moon, so bright it feels intimate, as if it belongs to us. And for a moment, the solar system plays a comforting trick. Venus is close. Sometimes at inferior conjunction, Earth and Venus slip onto the same side of the sun, and the gap collapses. It happens in a rhythm that repeats in familiar patterns, an almost echoing dance every 8 years, as if the cosmos is offering us a scheduled invitation. But closeness is not kindness. Venus is a world that looks like hope from far away and becomes a warning up close. A planet with an atmosphere so reflective it shines, and so thick it crushes. Pressure at the surface is about 92 times Earth's. Temperatures are hot enough to melt lead. Clouds are not water but acid. If Earth is a cradle, Venus is what happens when a cradle overheats, when a once possible climate tips, and cannot return runaway greenhouse oceans, lost geology, turned into a sealed pressure cooker. And still we go, because inside that hell might be the fossil record of an older, gentler Venus, billions of years ago, perhaps briefly habitable, before the thermostat broke. But again, the road there is not one road. Flybys can sprint. Orbiters must arrive humble. The first attempts were a kind of blind courage. The Soviet Venera, 1-inch 1961, started the story but fell silent. It likely passed tens of thousands of kilometers away after 97 days. Mariner 2 inches 1962 made the first successful flyby in about 110 days, proof that Venus was reachable and already revealing that it was not Earth's twin. Later missions like Pioneer, Venus, and Venus Express took longer, often 4 to 6 months, because getting there is not the same as staying there. An orbiter has to pay the breaking cost. And landing is where the planet shows its teeth. The only true surface images came from Venera 9 and 10, and even those victories were measured in minutes 53-65 before heat and chemistry finished the conversation. And when we pivot from Venus to Mars, the question quietly changes shape. It stops being only how long. It becomes, how do you live inside the long night between worlds? Long enough to arrive still human. Beyond Mars, the solar system stops feeling like a road trip and starts feeling like a long-haul exile. Jupiter appears first, not as a destination with a surface, but as a living machine. Storms wide enough to swallow continents. A magnetic field that can strip electronics bare. And around it a moon system that looks like a miniature solar system of its own. Europa, Ganymede, Callisto worlds that may hide global oceans beneath ice, sealed away from sunlight, warmed by tides, whispering the most dangerous question of all. If life can exist there, then maybe life is not rare. Maybe we've just been searching in the wrong kind of light. But Jupiter teaches you another version of the same old rule. Flybys can be fast. Pioneer and Voyager raced in, took their snapshots, and used Jupiter's gravity like a slingshot to escape toward deeper darkness. Galileo chose something slower and more costly, years of looping assists, just to arrive at a speed gentle enough to be captured to stay and study. New Horizons reached Jupiter in a little over a year, but it came as a passerby collecting a bonus of speed for its run to Pluto. Juno arrived to linger close passes. Deep questions about Jupiter's interior and magnetic heart, because the long science requires the slow arrival. And Saturn. Saturn is the planet that makes even scientists speak like poets. Rings so precise they feel artificial. A moon with methane seas. Another that vents plumes of salty water into space like an exposed artery. Cassini spent 7 years getting there. Years, because it needed to arrive not as a bullet, but as a resident. That is the price of belonging. Then come the ice giants Uranus and Neptune blue worlds, where blue is chemistry, not oceans. Uranus tilts on its side like a toppled god with a magnetic field that doesn't behave and a history that hints at ancient catastrophe. Neptune is the opposite: fierce winds, dark storms, a restless atmosphere. And here, the future begins to look like patience turned into policy, mission concepts, orbiters, atmospheric probes, because ice giants are common around other stars. To understand them here is to understand what most planets in the galaxy might actually be. The speculation is simple and sobering. We will not reach the outer worlds quickly by force. We will reach them by strategy. And then, at the edge of the tour, Pluto waits not as a planet that was demoted, but as a reminder that classification is a human comfort, not a cosmic truth. Pluto is small, yes, but distance doesn't care about size. Out there, the sun is no longer a blazing ruler of the sky. It is a very bright star, one light among many, cold enough that shadows feel permanent. Pluto's orbit is eccentric, stretched and stubborn, sometimes nearer, sometimes far, always slow. The gap between Earth and Pluto swells into numbers that refuse intuition: billions of kilometers. Light itself takes hours to cross it. Any command you send is not a conversation. It is a message in a bottle. New Horizons, small, fast, almost weightless by human standards, needed 9.5 years to arrive and steal those first close-up images. The pale plains, the frozen heart, the sense of a world that is less a rock and more a preserved chapter of the solar system's earliest eras. And if you imagine a crude ship, heavier shielded, stocked with life support and redundancy, time stretches again. Not years, decades. A human voyage to Pluto becomes something like a generational expedition, a choice to turn travel itself into a way of life, to accept that the mission is not the moment of arrival, but the long sequence of days that lead to it. Because that is what this journey has been quietly teaching us. Far is not just distance. Far is energy. To go from one planet to another is not to cross space like a flat desert. It is to change your orbit around the sun, to reshape your speed, your trajectory, your relationship with gravity. That's why Mercury can take longer than your instincts allow. That's why Venus can be near and still demand months. That's why Mars becomes a psychological trial. That's why Jupiter and Saturn reward patience, and why Neptune is less a place than a future era. And it's why gravity assists feel like art. They are the difference between a brief flyby, one photograph, one heartbeat, and a long season of discovery. Between a passing glance and a decade-long conversation. In a universe where braking is expensive, you learn to borrow momentum the way sailors borrow wind. Can we shorten the road? On paper, yes. Solar electric propulsion, tiny thrust over long time, turning patience into acceleration. Solar sails, photons pushing like an invisible river. Nuclear power for continuous thrust and deeper reach. Even bolder ideas, laser-driven sails, next-generation ion engines, propulsion that treats fuel not as a tank you burn through, but as a sustained relationship with energy. Each concept changes a different part of the equation. Some reduce cruise time, some make arrival cheaper, some shift the boundary of what possible even means. But whatever engines we build, the truth beneath them remains. The solar system is a moving clockwork, and travel is not merely distance. It is timing, energy, and the humility to meet a world on its own terms. So, when you look up at the night sky after this, don't see dots. See trajectories. See momentum. See worlds racing along invisible tracks, and a species small, stubborn, brilliant, learning to navigate them with math and patience, paying for every minute on the road with a reward that lasts centuries in our minds. And if you were allowed one stamp in your cosmic passport, one close-up moment before you return, what would you choose? The shadow of Saturn's rings sliding across its cloud tops. Europa's cracked ice hiding an ocean that has never seen the Sunday. Uranus tilted and quiet, carrying the scars of an ancient collision. Neptune's storms living and vanishing like thoughts. Which world would you spend your finite human time to truly meet? Because in the end, that is what "how long does it take" really asks. Not about rockets, about us.